In this video, we're going to go over two examples where we're going to draw a Lewis structure. We're going to use that to determine molecular shape, and then we're going to use that with electronegativity values to determine molecular polarity. And along the way, we'll also talk about bond order. Okay, so our first example is the molecule sulfur trioxide, SO3. So we've got a total electron count we can determine. So sulfur and oxygen are both in group 6, so they both have 6 valence electrons. We have one sulfur molecule and one sulfur atom and 3 oxygen atoms. So we've got a total of 18 plus 6 electrons, which is 24 electrons. Okay, so if we draw the Lewis structure, right, we would start with sulfur as the central atom because that is further from fluorine on the periodic table. And we would place our 3 oxygens around that. We make our 3 bonds. That is taking care of 6 electrons, but we still need to place 18 more. So we would start by putting those around the oxygens, okay? And that would get us to our 18 electrons, okay, that we need to place. So we've got 18 in lone pairs, 20, 22, 24 in our 3 bonds, okay? But the problem with this is that sulfur only has 6 electrons around it. So this is one of those cases where we need to take our one of our lone pairs and use it to make a double bond. Okay, so and you'll also notice that it doesn't matter which of these electrons we have, or which of these lone pairs of electrons, which of the oxygens that we take the lone pairs from. Okay, so I'm going to draw 3 versions of this structure, all equivalent, all having the double bond in, between a different oxygen and the sulfur. Okay. All right, so that is structure number 1, and I'm going to draw them vertically here. So structure number 2, I'm going to draw with the oxygen on the left having the double bond. Oops. Okay, and then in the third structure, I'm going to draw the oxygen on top having the double bond. And putting my lone pairs of electrons in. Okay, so that's our Lewis structure. All 3 of these are equivalent. So we have resonance. And we have 3 equivalent Lewis structures because they are, there's no difference in terms of if we turned the molecule around, we wouldn't be able to distinguish one from the other because they're all oxygen atoms that are having the double bond as an option. All right, so let's talk about bond order for a second. Okay, so when we have resonance structures and we're calculating bond order, first what we're going to do is we're going to say how many total bonds are there. Okay, so we've got 1, 2, 3, 4. So we've got 4 total bonds. And those 4 bonds are going to be divvied up between 1, 2, 3 outer atoms. Okay, so 3 outer atoms. Okay, so our bond order is 4/3, which is equal to 1.33, right? So the bond order of the SO bond, okay, so let's put this, the bond order of the SO bond in SO3, okay, is actually going to be 1.33. Okay, so the next thing we want to concern ourselves with is molecular polarity. Okay, so let's think about that for a minute. Okay, so first we have our Lewis structure, so we want to say what our molecular geometry is for this. Okay, and so we have, in this case, we've got 1, 2, 3 structural pairs connected to our central atom. Okay, so we have 3 structural pairs. And our sulfur does not have any lone pairs. So we have 0 lone pairs. And when we have 3 structural pairs and no lone pairs, what we have is we have trigonal planar geometry. Okay, so we have trigonal planar geometry, and we have SO bonds. Okay, so let's look at the electronegativity values for sulfur and for oxygen. So for sulfur, it's 2.5, and for oxygen, it's 3.5. So the SO bond is polar. Now, is the molecule polar? All right, I'm going to go over and show those bond dipoles on the bottommost resonance structure. So the oxygen is the more electronegative molecule. So I have my bond dipoles are going to point towards the oxygens. But my molecule is actually a triangle, right, with the sulfur in the center, and the oxygen atoms are at the edges of those. And so the bond dipoles actually go in this direction. So this is one of those 3-way tug-of-war situations, okay, where the bond dipoles all cancel out. And so the molecule is nonpolar. Okay, so our first example of SO3, we have a trigonal planar molecule with a bond order for the SO bond of 1.33, and it is trigonal planar geometry, and it's nonpolar. So now let's look at BrF3. Bromine and fluorine are both halogens, so they're in group 7. So we've got 7 valence electrons, we've got 1 bromine, and we've got 3 fluorines. So we have a total of 28 electrons in this case. Okay, so now what I'm going to do is I'm going to draw my Lewis structure. So I've got my bromine in the center, and my fluorines, I'm going to arrange around it. I'm going to start by adding my bonds. So that takes care of 6 electrons. So 6 bonding electrons. And so now we'll put the lone pairs on the fluorines. So each of those can take 6 lone pairs, because they have 2 that are in the bond. Okay, so that 6 times 3 is 18 lone pair electrons. Okay, so that gives us 24 electrons. So we still need to place 4 electrons. And Now, bromine, okay, is in the 4th row of the periodic table, and thus it is capable of having an expanded valence. So we can put those 4 electrons as lone pairs on the bromine. So I'm going to put those there. All right, so we have 4 lone pair electrons on the bromine atom. Okay, so now let's talk geometry. Okay, so for this we have 1, 2, 3, 4, 5 things attached. So molecular geometry. We have 5 structural pairs or 5 regions of electron density. Okay. And so the electron pair geometry is going to be trigonal bipyramid, okay? But 2 of those structural pairs are lone pairs, okay? So 5 structural pairs with 2 lone pairs gives us a molecular geometry that's a T shape. Okay. Now, when we're talking about whether our bonds are polar or not, we've got bromine has an electronegativity value of 2.8, and fluorine has an electronegativity of 4.0. So we are going to have polar bonds, and they're going to be polarized towards the fluorine. Okay. All right, so this is another case where we have 3 bond dipoles. So if you recall in SO3, we had 3 polar bond dipoles. In BrF3, we have 3 polar bond dipoles. But in the case of SO3, we have trigonal planar geometry. So all 3 of those things, okay, are going to cancel out. Here we have T-shaped geometry. So let's switch to blue and we'll draw that geometry. So our T-shape is we have our fluorine, 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 and the bromine is here. Okay, so this, as I've drawn it there, actually shows the real direction of those dipoles. Okay, so we've got this actual T shape. Okay, and so while these 2 dipoles cancel out, this one is still pointing in one direction, right? So 1 points left, 1 points right. Those cancel out. But now I have a net dipole. So this molecule is polar. So this is a polar because bond dipoles, don't cancel. And the reason for that is, again, because of this T shape. All right, so that's our examples of SO3 and BrF3.